In my last video, I talked a bit about how we have been able to determine what we know about exoplanets, and why our understanding of them is actually incomplete. There are a few things that I'd like to go into a bit more detail about in regards to exactly how a spectrum of light is used in order to determine the aspects of a star and potentially detect a planet. First, I wanted to clarify something that was a bit of an oversimplification. In the video, I mentioned that an image of a star may as well only be 1 pixel. But as we know from the beautiful images we get from telescopes, stars are never actually just 1 pixel in these images. In actual images, stars appear as disks and they often have points on them, which is why our cartoon image of a star looks like a star. This is due to various optical effects that take place within the camera or the telescope. Most of these have to do with the diffraction of light. Diffraction is the process where light bends when it encounters the edge of an obstacle in its path. The points of the star are formed by light diffracting off structures within the telescope. Usually this will be the supports of the secondary mirror, or potentially the aperture of the camera. The second way that diffraction affects the image is by blurring it. This is due to the diffraction from the edges of the telescope's main mirror, or lens, or whatever the collecting area is. As a result of this, telescopes with a larger diameter will cause less blurring and therefore allow smaller objects to be resolved. Assuming that we have a perfect mirror, the best possible image we can get from a star forms a pattern called an airy disk. This disk is a circular pattern with light and dark bands. Any point source will form a disk the same size in the image. So only features that would form an image larger than the disk are going to be able to be seen clearly. This is why, with current telescopes, it's not possible to directly image exoplanets. They are so close to their parent stars that the two disks would overlap and be unable to be seen separately. The other factor that affects the final image and stops a star from being a single pixel is that most cameras that are used in astronomy are CCD cameras, or charge-coupled devices. These cameras are electronic chips which are divided into pixels. Whenever a photon impacts on one of the pixels, it frees an electron and causes charge to build up in the pixel. The ability for each pixel to store this charge is limited, however, and if a pixel becomes full, the electrons that are generated can spill over into nearby pixels, often forming vertical streaks in the image, which ruin the aesthetic value of the image, but actually do not affect the scientific value. However, because of this, if there is a very faint object next to a very bright object, they will often be drowned out in the image. So while the star might not actually only be 1 pixel in the image, there is no actual detail that can be seen in the disk it creates. When we're trying to analyze the data, it may as well only be 1 pixel. Since it is very difficult to directly image an exoplanet, a variety of techniques have been developed to try and extract as much information as possible out of the images of the combined star system. One of the main ways that this is done is by looking for the subtle changes in a star's light that match the period of the planet's orbit. This does allow for information to be gathered about the planet without imaging it directly. However, care must be taken when making conclusions based on the information gathered in this way. Just because a change takes place with the same period of the planet doesn't necessarily mean that the light that we're seeing is coming from the planet. Also, detecting the signature of chemicals does not directly give us details on complex processes. However, it does give us extra information to add to our simulations. The fact that our explanations may not be 100% accurate doesn't change the incredible amount of information we have been able to gather about these planets. Well, this video got to be longer than expected. Next time I'll look at spectral lines and how we can actually tell what's going on these planets.